Thanks for inviting me to give a talk. So I'll be talking about some aspects of cardinality under the axiom of determinacy. But first, I just want to kind of say that the axiom of determinacy is kind of a very special, strong so the axiom of determinacy is kind of a very special, strong, choiceless, rigid theory of choiceless theory that kind of gives a very natural structure to sets that are kind of under the influence of determinacy. So in this case, these are just the sets which are surjective images of R. And the axiom of determinacy is rigid in one formal sense, right? So this result that I proved with Jackson and then fully generalized by Ikegami and Trang, that if you have a forcing P, which is a surjective image of R, so it's in the world of determinacy, and it's non-trivial, then it has to force the failure of AD. So you can't get independence results over AD, at least within the world of determinacy, by kind of these simple methods of forcing. AD can, it's kind of special in that it can settle combinatorial questions that, with the axiom of choice and even large cardinals, you can't necessarily settle. So the one we'll be talking about today is cardinal exponentiation. So let theta be the supremum of the ordinals that R surject onto, so it naturally can be regarded as the ordinal height of the determinacy world. So the main result is that there's like a complete classification of cardinal exponentiation in kind of a very natural way that you may as well call, like reasonably called a choiceless generalized continuum hypothesis. So the set of interest here is what I call PB kappa. So it's the set of all bounded subsets of kappa. And the main result is the first point here, that if you have an uncountable cardinal below theta and an epsilon less than kappa, then PB kappa does not inject into epsilon sequences of ordinals. And as an easy consequence of this, when you combine it with both-phase GCH, you get the following classification of cardinal exponentiation. So if you have infinite cardinals, alpha less than or equal to beta less than theta, and gamma less than or equal to delta less than theta, beta to the alpha injects into delta to the gamma if and only if alpha is less than gamma and beta is less than or equal to delta. And from this, if you give me any four infinite cardinals, and you can determine whether those cardinals are comparable or incomparable from this second relation. But the main result is the first one. Okay, so the first kind of natural step in classifying cardinal exponentiation is this kind of property that Steele defined called both-phase GCH at kappa. And it's the statement that there is no injection of kappa plus into the power set of kappa. And both-phase GCH and omega is actually a very common choiceless hypothesis that just says that there is no uncountable, well-orderable set of reals. And perhaps one of the most important consequences of both-phase GCH and omega is this result that everyone sees when they first learn forcing. So if both-phase GCH and omega hold, and you have an inner model of CFC and a forcing in that inner model, which is countable in the real world, then in the real world, you can find a p-generic filter for that forcing. How do you get these both-phase GCH? So if you have countable choice for the reals and the regularity property of the bare property and the perfect set property, then you can show that both-phase GCH and omega holds. And then using inner model theory, Steele and Woodin showed that both-phase GCH actually holds for every cardinal below theta. Okay, so starting with both-phase GCH and omega, you can, so among the four natural uncountable cardinals below R cross omega 1, this is the structure that it has, where all the arrows indicate strict injection. So in this choiceless context, cardinalities are always compared using the injection relation. Martin showed that omega 1 is a strong partition cardinal and omega 2 is a weak partition cardinal. Technically, we'll always use the correct type partition relation, which is the only useful form of the partition relation, but it doesn't matter here. For each epsilon less than or equal to omega 1, you can define a filter mu epsilon on omega 1 to the epsilon by saying that A is in mu epsilon if and only if there's a club, so that all epsilon sequences through that club is inside of A. Assuming like omega 1 has an appropriate countable exponent partition relation, this ultrafilter is countable complete, and by an elementary argument, you can show that omega 1 to the omega does not inject into power set of omega 1 across the ordinal. Similarly, if omega 2 satisfies an appropriate countable exponent partition relation, then omega 2 to the omega does not inject into the power set of omega 1 across the ordinal. And so you get the following structure among the 5 natural cardinals below omega 1 to the omega. But this is not exactly the most ideal proof because we're using partition properties, and of course there are singular cardinals like omega 3, which are not partition cardinals. So there's another way you can approach this. So we define this notion called primeness. So X is prime if for any two sets A and B, if X injects into A Cartesian product B, then X already injects into A or X already injects into B. So under AD, you can show that R and R mod the E0 equivalence relation are prime. If kappa satisfies an appropriate countable exponent partition relation, then omega sequences through kappa is prime. So omega 3 is the first singular cardinal, but using Martin's ultrapower analysis, you can show, for instance, that omega 3 to the omega happens to be prime. And if kappa to the omega is prime, then it's easy to see that for every delta less than kappa, kappa to the omega does not inject into the power set of delta across the ordinals. So in particular, we now know that like omega 3 to the omega does not inject into the power set of omega 2 across the ordinals. It's quite possible that every cardinal kappa to the omega is prime, but we don't know how to prove that. And later I'll like mention another way that you might try to prove something like this. Okay. Now, Woodin defined a very natural subset of omega 1 to the left than omega 1, which he called S1. So this is the collection of all F in omega 1 to the left than omega 1. So that sup of F is omega 1 of L of F. You can show that R injects into S1 and omega 1 does not inject into S1. And under some determinacy assumption, Woodin must have known that S1 does not inject into omega sequences through omega 1, and omega 1 to omega is strictly smaller cardinality than the bounded subset of omega 1. And since omega 1 is regular, that's the same as omega 1 to the left than omega 1. And hence you have this picture of all the cardinals that we've mentioned so far. So I don't think Woodin included a proof of this result in his paper, so I don't actually know how he proved this result, but he does prove a very technical dichotomy result that I don't think formally actually implies this. Because I don't, we spent some time trying to find proofs of this result and different proofs that could be generalized to higher cardinals. So the first kind of natural proof that we found involves infinity Borel codes. So I won't give the details here, and I'll tell you, for now, an infinity Borel code is more or less an ordinal which gives you a highly absolute definition for some set. I'll give you more details of this argument in a different context, and I'll tell you what infinity Borel code is later. But what's the point of the infinity Borel code? So suppose you really did have an injection from PB omega 1 into omega 1 to the omega. So PB omega 1 and omega 1 to omega are essentially hereditarily countable objects. So using some collapse forcing idea, it's not too hard to get infinity Borel codes in a reasonable sense for these type of functions. So if you have any inner model M with an infinity Borel code for phi and phi inverse, then M and all generic extensions of M, in fact, all external models of M are able to see a true fragment of phi, and this will allow us to do some kind of forcing argument later, which I'll sketch later. But this is kind of the argument. The template for this argument is what we want to generalize. But let me show you some of the other ways we can do this. Using descriptive set theory and partition relations, we prove a continuity property for functions from omega 1 to the epsilon into omega 1. Later, I'll say what that thing is. But from this, we have a proof under AD that omega 1 to the omega is strictly smaller than PB omega 1. Using Martin's ultrapower analysis, you can extend this to show that PB omega 1 does not inject into omega n to the omega, and even omega sub omega to the omega. And then using more point class arguments kind of specific to omega 1, if you add on DCR, then you can show that PB omega 1 does not inject into omega sequences of ordinals. of course, we want to get rid of that DCR, and we want to do this for larger cardinals. So to do this, we actually have to prove a pure combinatorics result. So if kappa satisfies the epsilon times epsilon partition relation, cofinality of epsilon is omega, which is important, and you have a function from kappa d epsilon into the ordinal, then it has the following continuity property. So there's a delta strictly less than epsilon and a club subset of kappa, so that for any f and g in C to the epsilon, if f and g agrees on their delta of initial segment and they share the same sup, then the value of the function at f is equal to the value of the function at g. Now, continuity is nothing more than a very well-controlled failure of injectivity, right? So we can use this continuity result to show that if kappa is a weak partition cardinal, then PB kappa does not inject into omega sequences of ordinal for all epsilon less than kappa. And since under AD, omega 1 has a strong partition property, this gives you a AD proof that PB omega 1 does not inject into omega sequences of ordinals. But then, for some times, I've kind of been interested in these two kind of questions. So S1, as I mentioned before, is a natural set, but it's not necessarily a combinatorial set, right? So you can't really use partition properties to address whether S1 injects into omega sequences through the ordinals. So one question is, can you prove this under AD? And if you want to classify the cardinal exponentiations, you're going to have to look at the PB kappas, where kappa are larger cardinals and maybe even singular cardinals. And the first one we don't know at the moment is whether PB omega 3 injects into omega 2 sequences of ordinals. But both questions kind of address the same type of problem. How do you address these type of questions without assuming functions, which here may be highly uncountable objects, have infinity Borel codes? So let's look at the first one. There's this lemma of Woodin that actually gives us the necessary capturing result using category. So if let's say all subsetsable polar spaces have the bare property in both HGCH and omega holds, let X be a set with an ODX well ordering of X, let P be a forcing in hot X, which is countable in the real world, then there's actually a whole meager set of generic, so that, which are generic over hot X, so that hot X adjoint G is hot sub X and G. And then this is the main argument that we will try to generalize for the rest of the talk. Okay, so under these assumptions, you can show, which of course holds under AD, PB omega 1 does not inject into omega sequences of ordinal. So let's suppose you have an injection from PB omega 1 into omega sequences of ordinal. So let G be a generic for whole omega plus omega double plus as computed in hot sub phi. This is a countable forcing in the real world by both HGCH, and hence by that lemma, you can find a G so that hot phi adjoint G is hot sub phi and G. Phi G is clearly OD from phi and G, and hence it belongs to hot sub phi and G, but we know that hot sub phi and G is hot adjoint G. This forcing adds no new omega sequences. This is countably closed, so that means phi of G must belong to hot sub phi. But if phi of G is OD sub phi, then phi inverse phi of G is OD sub phi, and hence G is in hot sub phi. And you just put the generic into the ground model, which is not possible. So this is the argument I want to generalize for the rest of the talk. But let's finish up that thing about S1. So to do this kind of argument for S1, you just need to kind of strengthen Woodin's lemma a little bit. So again, same setting as before, let Q be a forcing in hot sub X, which is countable in the real world. You can even find a co-meager set of generic G so that it has the property that for any forcing projection of Q onto P, where the projection actually belongs to hot sub X, hot sub X adjoin the P upward closure of the image of G is hot sub X, and the G upward, the image of G upward closure in P. Because you're a forcing projection, that thing actually is a P generic. And then under the same assumptions, you can show S1 does not inject into omega sequences of ordinals, and it's basically the same argument, but the fourth thing you want to use is the collapse of the ordinal less than omega 1 to omega in hot sub phi. The reason why you need this kind of strengthened lemma is that phi of G is an omega sequence, right? It doesn't necessarily belong to the ground model, but it belongs to this restriction of G to some initial segment, right? That comes from some kind of forcing projection. But other than that, everything, it's basically the same argument. And we can also use this idea to get another proof of that. So under these assumptions, omega 1 to the omega does not inject into power set of omega across the ordinal, and hence r cross omega 1 is strictly less than omega 1 to the omega. So the fourth, it's basically the same argument, but the fourth thing you want to use is, so first fourth with collapse omega 1r, so its only purpose is to get you CH. Then fourth with the Namba forcing over that extension. But the entire point is that this two-step iteration adds no new real, but it adds a new omega sequence cofinal through omega 2. There are not too many ways to do this. You might want to try to use prickly forcing, but under these assumptions, there might not be any measurable cardinal. And even if you're in L of R, the Hod analysis says, like for instance, in L of R, there is never a prickly generic extension for a measurable cardinal of Hod. So there's not too many ways to do this. By the way, these look like classical regularity properties, and this is just a simple combinatorial cardinality inequality. But this is, at the moment, the only proof I know of this resolved. And in some sense, I think this is the correct proof to use if you want to generalize it higher up. Okay, so now let's get into the main result. So suppose you had an injection from PB kappa into epsilon sequences of ordinal. Now I want to imitate that proof from before, so that means I need to solve two problems. First, in the real world, I would need to have a generic filter for col epsilon plus epsilon double plus of m over m. I need the filter to actually exist. And I need to solve this capturing problem. For such a generic G, I need m of G to at least be closed under the phi function, and I need m to at least be closed under phi inverse. So let's address the filter existence problem first. So if you let beta be an ordinal and m be some inner model of DFC, so let f be a function in the real world from beta into m, and let's say that, let's call it a pseudo member of m if for every alpha less than beta, the initial segment f restricted to alpha is in m. So assuming, you just need some appropriate form of countable choice. But let's say kappa and lambda are less than theta, the cofinality of kappa and the cofinality of lambda is omega, and m is an inner model of CFC. Suppose for every delta less than lambda, you have a surjection of kappa onto delta, which is a pseudo member of m. Then you actually have a surjection of kappa onto lambda, which is a pseudo member of m. And this is just some simple combinatorial argument. You just patch together those omega many pseudo member surjection in such a way that it's still a pseudo member surjection. Now, assume m is an inner model of ZFC and epsilon is an infinite ordinal. Suppose the true cofinality of epsilon plus an m, the true cofinality of epsilon double plus an m, and the true cofinality of epsilon triple plus an m is omega, and m satisfy 2 to the epsilon plus is epsilon double plus, and 2 to the epsilon double plus is epsilon triple plus, then you can find in the real world a generic for col epsilon plus epsilon double plus of m over m. And the important point is that using the previous lemma, under these hypotheses, you can find a surjection of epsilon plus of m onto the collection of all dense subsets of collapsed epsilon plus epsilon double plus of m in m, which happen to be a pseudo member of m. But then you can do the usual trick of forming a generic filter by epsilon plus of m many steps. With each step, you just get one condition into the next dense set. And this is possible because every initial segment of my enumeration is inside the model. So using the epsilon plus closedness of the model, I can actually find another thing under it. And then you might be wondering, how do you even get models like this? So Hod-type models of certain determinacy models will satisfy this by the directed system analysis. Okay, so that's solved the generic filter problem if I can find the appropriate m. So I need to solve the capturing problem. Now I'll define what infinity-Borel code is. So let B infinity be the collection of infinity-Borel codes. So this is nothing more than a pair S phi, where S is a set of ordinal and phi is a formula. Fix the cardinal kappa once and for all. Now, if P is an infinity-Borel code, then we'll let B n sub P be the collection of functions from kappa to the omega to the n that satisfy that infinity-Borel code. And if you have a function from kappa to the omega to the n, f, and you have a subset of infinity-Borel code, then we'll let G and Ft be the collection of all infinity Borel code that F lands into. Now fix a set Z with an ODZ well ordering of Z. So, okay, maybe I won't go through the full detail of this, but okay. So the fourth thing you want is the collection of ODZ infinity Borel code forcing for kappa to the omega to the n. This is a proper class, right? So there's some standard trick of picking like the minimal element in this natural equivalence relation. Order P, say P is less than Q if the set coded by P is less than the set coded by Q. You know, the largest element is the code for kappa to the omega to the n. So this Bn is the n-dimensional ODZ infinity Borel code forcing, and we'll let Bz hat be the code set for all of these forcing. It's some set of ordinal in ODZ that codes all information about all these forcings. Now, if you have an element of kappa to the omega to the n, let G sub y be the collection of all infinity Borel codes in this B sub n, so that y lands into the set coded by that infinity Borel code. So in any intermodel M of Hod Z, which contains the code set for all of these forcings, you can show that G sub y is Bn generic over M, and M sub y is M of G sub y. So this is if you know what Vopanka forcing is, this is very similar, right? But what's special is that this last condition is not something that Vopanka forcing necessarily satisfies. So that's kind of the benefit of this OD infinity Borel code forcing. Okay, now let X be a set. Let nu be a ultrafilter on P omega 1x, which is just the collection of all countable subsets of X. So nu is said to be fine if for every X in X, the collection of sigma that contain X is big. It's nu is normal if for every function from P omega 1x to P omega 1x, if the collection of sigma so that phi of sigma is non-empty and inside of it, and it's a subset of sigma is large, then there is some X so that the collection of sigma so that X is in phi of sigma is large. And a super compact measure on P omega 1x is a countably complete fine normal measure on P omega 1x. So under AD, there's no problem getting countably complete fine measures. So if you pick a surjection of R onto kappa, you can create some kind of natural function and use it to do the Woodin-Kiesler push forward of the Martin measure on Turing degrees, and its complexity will be closely connected to how complicated that surjection you chose. And then Harrington-Keckrich showed that if kappa is below a Suslin cardinal, then there is a super compact measure on P omega 1 kappa, and Woodin showed that it's actually unique, so it's absolutely ordinal definable. So let pi nm be the projection of kappa to the omega to the n to kappa to the omega to the m. So if you assume both HGCH at omega, and you have a fine countably complete measure on P omega 1 kappa, such that the ultra power of the universe by that measure is well founded, then there is this OD nu function upsilon, so that pi nm of the n-dimensional set coded by P is the m-dimensional set coded by upsilon Pmn. So in other words, upsilon is an OD nu uniform way of transforming an infinity Borel code for an n-dimensional set to its projection onto M. And let me just give a little detail of how to do this. Okay, to simplify things, let's M be 1 and N be 2. So let P infinity be the image of P under the ultra power map. Let B hat infinity be the ultra power of the map that takes sigma to the code set of the ODZ infinity Borel code forcing, but as computed in the intermodel LP sigma. Let C sigma be the collapse of the two-dimensional ODZ infinity Borel code forcing, and let C infinity be the ultra power of the map that takes sigma to C sigma. And then let J star be J nu restricted to kappa, which is a set of ordinals. So note that although Wash's theorem doesn't hold for the ultra power of the universe, it does hold for ultra powers of these local L-type models. And hence you can show that P infinity takes the form S infinity phi for some formula. So I claim that X belongs to pi 2, 1 of the two-dimensional thing coded by P, if and only if L of P infinity, the B infinity hat thing, J star composed with X models that one of the C infinity forcing forces that there exists a y so that L of S infinity J star composed with x, y thinks the formula phi of S infinity J star composed with x, y holds. So I just want to point out what is special about you. So remember, this result is for omega sequences of ordinal. What's kind of special is that when you have an omega sequence of ordinal, J of a omega sequence is the ultra power composed with that omega sequence, right? So that's why I'm kind of emphasizing this by writing it as J star composed with X. But now, if you can use this claim, so using those three sets of ordinal, P infinity, B hat infinity, and J star, you can cook up some kind of formula to turn this into an infinity Borel code for pi 2, 1 of the set coded by, which is the OD nu. Now let's assume AD and DC are, and Z is some set of ordinals so that V is LZR. So in models of this form, all ordinals below theta have a pre-well ordering, which is ODZ, and hence that fine measure nu is ODZ, and hence that function upsilon is OD. And then you can define forcing projections between Bn and Bm, right? You just take you just let pi nm of p be basically what upsilon p of mn says it should be. So now once you have this directed system of forcing projections, you can define the directed system. So you can let b omega be the collection of all functions on omega so that p of n is always in b of n. For any m less than or equal to n, pi nm of p of m is equal to p of m, and it has this kind of finite support condition. So for any k, there is some capital N, so that for any k bigger than n, the k-dimensional set coded by p of k is the capital N-dimensional set coded by p of capital N cross r n minus k, all the remaining dimensions. So this this directed system of infinity Borel code forcing has naturally an omega sequence through kappa to the omega, and let tau omega sub n be the name for the mth term of that generic sequence. Let the symmetric kappa to the omega be the name for all those tau n omegas. And if you restrict to just the reals, we'll just call that the name for the symmetric reals. And like before, let B vector be this OD set of ordinals that code everything all the information we have above about the directed system. So then in this setting, if you have an inner model of, it should be HZ, containing the code set for the directed system, and you have any n in omega, x in kappa the omega to n, any y in m of x, and any a in m of x intersect Ly of kappa the omega in any formula, what Ly kappa the omega thinks about a formula phi of a holds if and only if m of x thinks that one of the directed system forcing quotient out by the n-dimensional generic induced by x forces that Ly to symmetric kappa thinks phi of a is true. So the significance of this is that truth about something in the real universe essentially is captured by truth inside of a certain inner model of ZFC. What's the point of this y? So often there's kind of a very natural set z, but z is probably not ODZ, right? So for instance, if z is like an uncountable set of real or an iteration strategy for the mouse, it's going to be ODZ, but it's not going to be in HZ. But very often there is some set y which is in HZ, so that ODZ is equal to ODY. That's important, right? Because if z is not actually, so M is an inner model of HZ, right? So if y is not actually in HZ, there's no way that I can use that y in that second forcing statement. Okay, one more definition. So if you have a forcing P, say that a P filter F is countably generated if and only if there's a countable subset of F, so that the P upward closure of sigma is F. So this is kind of the main capturing result we need, and it's kind of the analog of that Woodin result for category. assume the same setting. Let's say that you have a y in hod z, so that ODZ is ODY. Let P be a forcing in hod z. Suppose there's a Suslin cardinal kappa, so that hod of z thinks the size of the forcing is kappa. Let F be a countably generated P filter. Then hod z adjoint F is hod of z and F as a parameter. So let me, so it's kind of an ugly little formula, but let me say what it is, and now I'll emphasize the important point. So since kappa is less than a Suslin cardinal, by Woodin's result, there is a supercompactness measure on kappa. So then you can transfer that to an ODZ supercompactness measure on P omega 1 P. Now, if you have a formula phi of VW, there's going to be a derived formula phi tilde of x, y, and z. So, and it'll say that y is a forcing, x is a function from omega into y, and phi of the y upward closure of the image of x and z holds. Pick any a in hot sub z. Let h dot denote the canonical collapse of j image f name for the surjection of omega onto j image f. So the claim is that phi of fa holds if and only if L of j this, that, or another thing, j image f model 1 of the collapse of j image f modeled L of j blah, 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 h dot modeled 1 of, okay, so j nu of b omega is still a collection of infinity Borel codes, right? So I can, using h dot, I can derive its canonical filter consisting of all the infinity Borel codes that H lands into, take the remainder forcing of that. It is forced that Ljy of J of the symmetric real model phi tilde of H, J of P, J of A. Okay, so, okay, you know, this is some consequence of, you know, ultimately proved by Wasser's theorem. But let me just emphasize the important point, though. So the forcing is assumed to be, the filter is assumed to be countably generated, right? So by the fineness of the supercompactness measure, for almost all countable set, it contains the essential information about the filter, enough to upward generate that filter. I want to use the previous result, which only holds for omega sequences, right? So that's why I introduced that collapse forcing, right? So this will introduce a omega sequence enumerating a sufficiently useful countable set. What's the point of the supercompactness, in other words, the normality? So if you have so almost all countable sets contain essential information about the filter, right? So, but when you have a normal filter, the map that goes from sigma to f intersect sigma, its ultra power is mapped to j image f. So j of f, these are uncountable objects, right? J of f is probably not going to be in hod sub z adjoint f, but j image of f is something that hod sub z adjoint f can see, right? So that's I mean, I want to emphasize everything else is j of something, but that it's important is j image f. Wherever it appears. So now this thing is something that can be seen inside of hod zf. So you know, using this kind of statement, you can capture an ODZF statement inside of hod zf, and then by some standard argument, you can prove that these two hod things are the same. Yes. Okay. So I guess now we're ready to prove the main theorem. So let me do it in the easy case of L of R. So assume kappa is an uncountable cardinal below theta, and epsilon is less than kappa. So we want to show that PB kappa does not inject into epsilon sequences of ordinal. So suppose the result is not true. By sigma 1 reflection, you have a counterexample, i.e. an injection from PB kappa into delta the epsilon, which lands in L delta 2 1 of R. And then by absoluteness in the Moshkavakas coding lemma, you can show that actually still is an injection in the real world L of R. Everything in a model of the form L of R is OD from a real, so fix a real x so that phi is OD sub x. So Steele showed that hod sub x satisfies GCH, and the true cofinality of all successor cardinals are omega. So by that generic filter existence thing, I can find a generic G, which is col epsilon plus epsilon double plus as computed in hod generic over hod sub x. Delta 2 1 is a Suslin cardinal and certainly bigger than the size of the forcing in hod sub x. since the true cofinality of the successor of epsilon plus in Haas of x is omega, you can show that the generic filter is countably generated. So then we can use the capturing result we can use the capturing result we just proved. So again, this is just like that other result from before. Phi of g is clearly OD from x and g, so it belongs to Ha sub x and g, which we, by our capturing result, is Ha sub x adjoin g. This forcing adds no new epsilon sequence, and phi of g is an epsilon sequence, so it has to belong to the ground model Ha sub x. And if phi of g is ODX, then phi inverse phi of g is also ODX, so g is ODX, and hence g belongs to the ground model Ha sub x. And again, you get a contradiction by getting the getting the generic into the ground model. Note that I don't need to do any of the z and y business because x is in Ha sub x. All right. So, but it's going to be more tricky when you want to prove it under 80 plus. So same result. So I just want to sketch how to get into the setting where you can do what we just did. Assume the result is false. So using Woodin's 80 plus Suslin co-Suslin reflection, if you have a counterexample, you can find a counterexample phi from PB kappa into delta to the epsilon, which is coded by a Suslin co-Suslin set. This is basically the only genuine use of 80 plus that's used. Everything else is under 80 plus DCR. But this is a very substantial use of 80 plus. And then then you have to use this kind of gamma Woodin setup. So fix 5 point classes that are tightly connected to each other, right? They form this life-phase analytical hierarchy of good point classes closed under there exists R, not for all R, and contains the coset A. Let T4 be a tree that projects onto the complete gamma 4 set, and let T1 and U1 be trees that project onto the complete gamma 1 set in its complement, which is constructible in LT4. So Woodin showed that for some real x, Haas of LT4 of x with parameters from T4 thinks the omega 2 of LT4 of x is a Woodin cardinal. And starting from this, in that paper of steel by the Woodin mouse set thing, you can find some models M, some ordinals alpha and eta, some well ordering of LP eta, and some countable transit model M, so that you have an elementary map from M into this L alpha, LP eta, WT1, U1. But moreover, you can show that this M has an iteration strategy that chooses pi realizable branches, and you can actually kind of recognize this branch using this C gamma 1 function, the collection of sets which are delta 1 and some countable ordinal. And let T and U be something so that pi TU is mapped onto T1 U1. So the Z that we want, the natural Z that we want will be M union the well ordering with the iteration strategy. So this thing is a core structure, but I guess Benny and Farmer observed that if you restrict the iteration strategy to nice extenders, you can do some form of comparison. And this will allow you to form a directed system of countable iterates of M by the strategy for the nice trees. So let T infinity, U infinity be the image of T and U. And using the fact that all these things are pi realizable branches, you can show that T infinity, U infinity project onto the complete gamma 1 set in its complement. And it's clear that T infinity, U infinity is OD from Z and LZR. But again, Z contains an iteration strategy, so it's not actually in Haas of Z. So we replace Z with the set Y, which is M union W, T infinity, U infinity. Y is in Haas of Z. And as we mentioned, sigma is kind of guided by the C gamma 1 operator. And since T infinity projects onto the complete gamma 1 set, sigma is OD sub Y. And from that, you can show that OD sub Z is OD sub Y. If you look at these hybrid strategy sigma mice, you can show that these Haas of Z and Haas of Y are a directed system of these mices. So by the Steele analysis for the model Haas of Z of LZR, you can show that it satisfies GCH, and the true cofinality of successor cardinals is omega. And now you're in the setup to do exactly what we did before and finish it just like what happened before. Yeah, so that's the proof of the main theorem. And there's yeah, just want to remind you, from this main theorem and both HGCH below kappa, you can easily get that cardinal exponentiation result that I mentioned at the beginning of the talk. If you repeat kind of this argument with some additional new ideas, you can show that if kappa is a singular cardinal, then PB kappa union kappa to the cov kappa is strictly smaller than power set of kappa. And at a first glance, you would think that this is almost obvious from the main theorem, and it is if you have some regularity properties. So with Steve and Nam, we kind of defined the notion of cofinality and regularity in this choiceless context and studied the cofinality for power set of omega 1. But one of the things we can prove is that the power set of omega 1 is what we call ordinal regular, which means that if you split the power set of omega 1 into ordinal many pieces, at least one of the pieces must have full-size power set of omega 1. Unfortunately, we don't even know, for instance, whether the power set of omega 2, right? So, this is actually really a property of a strong partition cardinal. But if you have even a weak partition cardinal, we don't even know if it's too regular. But if it was too regular, it's kind of easy to see that theorem implies. If power set of kappa was too regular, it's kind of easy to see that theorem follows in the main theorem. When kappa is singular, PB kappa and kappa to the less than kappa are not the same set. Now, if power set of kappa was kappa regular, then we could use the main theorem to give a positive answer to this question. So these we still don't know. Is omega 3 is the first singular cardinal. Is omega 3 to the less than omega 3 strictly smaller than the power set of omega 3? Does omega 2, the power set of omega 2 inject into the less than omega 2 length sequences of ordinals? Yeah, so one way to resolve this would be to figure out I mean, it's not an unreasonable conjecture that maybe the power set of any ordinal is fully ordinal regular, or at least